Welcome back to my class in Abstract Algebra. Today we will discuss the group of permutations. First, we have to recall and define two important concepts, permutation and composition of function. We can define a function from a set of objects to the same set of objects by finding the permutations of the objects in the given set. And in the group of permutations, the operation involved is known as composition of functions. So we have to define permutation and composition of functions. In particular, we have to define permutation case 1, that is permutation of n different or n distinct objects. Permutation is defined as the arrangement of objects with regards to order. That is, in a permutation or arrangement of objects, the order of the objects is important. It is the order of objects that makes one permutation different from another permutation. And there are three cases of permutations. The first case is where you have the permutations of n different objects taken all at a time. And the second case of permutation of n different objects, but not all of them are to be arranged at one time, and only a subset of them are to be arranged at a time. So that's case 2, permutation of n different objects, small letter n, taken r, small letter r, at a time, where the small letter r is less than n. And the third and last case of permutation is where we have the arrangement of n objects that may not be all distinct, which means that some of them are repeated, some of them are alike. And we have permutations of n objects, some of which are alike. And that's case 3. But the case of permutation that we will need for the group of permutations is permutation case 1, the arrangement of n different objects taken all at a time, or n distinct objects taken all at a time. And the number of arrangements of n different objects taken all at a time is given by n factorial. We read this as n factorial. The factorial notation was first used by the Swiss mathematician Christian Kramp. And n factorial is defined as the product of all integers from n down to the smallest positive integer, 1. Hence, n factorial is equal to n multiplied by n minus 1 times n minus 2 up to 3 times 2 times 1, where n here is a positive integer. We take an example. Consider the set S with elements 1, 2, 3, and we find the permutations of these numbers 1, 2, 3, or the elements of set S. For this particular set, and the number of elements in S is 3. And according to permutation case 1, if the number of arrangements of n distinct objects is n factorial. In this example, there are three objects, there are three numbers that are all different. And the number of arrangements or permutations of these three different objects is n factorial, where n is 3. So this is equal to 3 factorial. And 3 factorial is equal to the product of the positive integer 3 up to the smallest positive integer, which is 1. Thus, 3 factorial is equal to 3 multiplied by 2 multiplied by 1. And if you multiply 3 by 2 by 1, we get 6. Therefore, there are 6 permutations of the numbers 1, 2, 3, or there are 6 arrangements of the numbers 1, 2, 3. And we enumerate them. The original arrangements of these numbers 1, 2, 3 in ascending order 1, 2, 3 is the first permutation of 1, 2, 3. Next permutation is 1, 3, 2. This permutation and this permutation are different because, and the order of the numbers 2 and 3 makes the difference between these two permutations. That is why we say that order is important in permutation. Permutation is defined as the arrangement of n distinct objects taken all at a time. Or permutation is the arrangement of objects with regards to order. Another permutation of 1, 2, 3 is 2, 1, 3. Another permutation with 2 as the first number in the arrangement. Now we have already enumerated 4 permutations of 1, 2, 3, and we only need 2 more permutations of 1, 2, 3. And we list down the last 2 permutations of 1, 2, 3, each beginning with the digit 3. And these are all the permutations of the 6 permutations of the numbers 1, 2, 3 elements of set S. And all these permutations are different, and it is the order that makes the difference between 2 permutations. Now, I said that earlier that we can define a function from a set of objects to the same set of objects using permutation. We let P1 denote the function that assigns the elements of set S to the first permutation of the numbers 1, 2, 3. So P1 here is a function from set S to set S, where 1 is assigned to 1 under the function P1, 2 is assigned to 2 under the function P1, and 3 is assigned to 3 under the function P1. Again, we define a function P1 from set S to set S. Under the function P1, the image of 1 is 1. 1 is assigned to 1. Under the function P1, the image of 2 is 2. Under the function P1, the image of 3 is 3. Thus, the function P1 assigns each element of set S to itself. And this second row of this matrix is the first permutation of the numbers 1, 2, 3. We define another function from S to S, but from set S to S, but now we assign the numbers 1, 2, 3 to the numbers in the second permutation of the numbers 1, 2, 3. And we shall call this function P2. P2 is also a function from set S to S. The domain is consists of the numbers 1, 2, 3. And the images of these numbers 1, 2, 3 are given by the second permutation of the numbers 1, 2, 3, which is 1, 3, 2. Hence, we have defined another function denoted by P2 from set S to set S. Under the function P2, the image of 1 is 1. 1 is assigned to 1. The image of 2 under the function P2 is 3. 2 is assigned to 3. The image of 3 under the function P2 is 2. 3 is assigned to 2. Now we define the third. So if you have 3 objects and there are 6 permutations of these objects, you can define 6 functions from S to S. And the third function we denote by P3, that is a function from S, and the elements of S, 1, 2, 3 are assigned to the third permutation of the numbers 1, 2, 3, which is 2, 1, 3. P3 again is a function from set S with domain 1, 2, 3 to itself, to set S with elements 1, 2, 3, except that they are in different arrangement or permutation. Under the function P3, the image of 1 is 2. 1 is assigned to 2. And 1 is the image of 2 under the function P3 because 2 is assigned to 1. 3 is called the image of 3 under the function P3. 3 is assigned to itself. And we define the last 3 functions from set S to set S, and we denote these functions by P4, P5, and P6. Now, the function P4 is a function from set S, but the images of these elements of S, 1, 2, 3 are assigned to the numbers in the fourth permutation of 1, 2, 3, which is 2, 3, 1. Thus, 1, 2, 3 are assigned to 2, 3, 1 respectively. The function P4 is a function from set S to set S, and the images of 1, 2, 3 under the function P4 are 2, 3, 1 respectively. The function P5 is also a function from set S to set S, and the elements of, but in this function, the images of 1, 2, 3 elements of set S are the numbers in the fifth permutation of 1, 2, 3, which is 3, 1, 2. Under the function P5, the images of 1, 2, 3 are 3, 1, 2 respectively. Thus, P5 is a function from set S to set S. And P5 of 1 is 3, that is 3 is the image of 1 under the function P5. 1 is the image of 2 under the function P5. And P5 of 3 is equal to 2, or 2 is the image of 3 under the function P5. 1 is assigned to 3, 2 is assigned to 1, and 3 is assigned to 2. And the sixth and final function that we can define from set S to set S is a function where the images of the elements of S, 1, 2, 3 are assigned to the numbers in the sixth and final permutation of 1, 2, 3, which is 3, 2, 1. So P6 is P sub 6 is another function, the last and sixth function that we can define from set S to itself, where the images of the elements of set S are 3, 2, 1 respectively. And 3, 2, 1 is the sixth and last permutation of the numbers 1, 2, 3 elements of set S. Now, in the group of permutations, the elements of the group, the elements of the non-empty set in the group are these functions P2, P1, P3, P4, P5, and P6. And the binary operation for this group of permutation, for this group with the non-empty set consisting of the 6 permutations or the 6 functions from S to S, is the composition of function, which we now define. For us to define composition of functions, we need to have two functions, and we denote these two functions as function f from set A to set B, and function g from set B to set C. Let f be a function from A to B, and g be a function from B to C. Then the composition of these functions f and g, denoted by f circle g, you read as f circle g, is defined as follows. The composition of the functions f and g, denoted by f circle g, is a function from A to C. And when the function f circle g is evaluated at x, f circle g of x is equal to g of f of x. You notice that A is the domain of the function f, and the domain of the composition of the functions f and G is A, the domain of f. And C is the codomain of the function G. And the codomain of the composition of functions f and g is C. When you want to evaluate the composition of two functions f and g at a particular value of x, first you evaluate the function f at x, and the result you use to evaluate the value of the function g at this value of the function f at x. This definition would be easier to visualize if we use a diagram. We start with f. F is a function from A to B. So we draw in diagrams the sets A and B. The function from A to B is the function f. Now we take any arbitrary element from set A and we denote that by small x. If we find the value of the function f, or this x, or if we evaluate the function f at this particular value of x, then the image of x will be in the codomain of the function f. So the function f assigns to each element of its domain, set A unique element of its codomain. And this element assigned to x is the image of the image of x under the function f, and is denoted by f of x. Now the function g is a function from set B to set C. If we find the image of this f of x, element of set B, under the function g, then we would get the image of f of x under the function g is given by g of f of x. That is, the function g is evaluated at this element f of x of B. Now, the composition of the functions f and g, denoted by f circle g, is a function from set A to set C. And you can see that if this element of x is, if the composition of f and g, f circle g, is evaluated at this element x of A, that is f circle g of x, we would get g of f of x. The function f is evaluated first at x, and then the function g is evaluated at the value of f of x. And this element g of f of x is in set C, the codomain of g, and also the codomain of the composition of the functions f circle g. we take some examples using these functions of the functions from set S with elements 1, 2, 3 to set S, but the images of S are assigned to elements in the permutations of 1, 2, 3, the elements of S. For our examples of compositions of functions, consider the following. Find the composition of functions P2 and P3, where functions P2 and P3 are functions from set S to set S. Specifically, they are given by the following permutations. P2 is a function from set S to set S, but the elements of set S are assigned to these numbers in the second permutation of 1, 2, 3. P3 is also a function from set S to set S, but the images of the elements of S, 1, 2, 3 are assigned to these numbers in the third permutation of 1, 2, 3. We also find the composition of the functions P5, P4, and P1. And we start with composition of P2 and P3. P2 is the function defined by this matrix 1, 2, 3 and 1, 3, 2. And P3, a function from set S 1, 2, 3 to the same set 1, 2, 3. P2 is a function from S to S, and P3 is a function from S to S. Therefore, the composition of functions P2 and P3 is also a function from S to S. So the domain of the composition of P2 and P3 is the same set with elements 1, 2, 3. And we start by finding the elements of 1, 2, 3 under this composition of functions P2 and P3. We start with 1. By definition of composition of function, the composition of P2 and P3 evaluated at 1 is given by P3 of P2 of 1. And P2 of 1 is the image of 1 under the function P2. Or P2 of 1 is the image assigned to 1. By inspection of P2, this is P2. 1 under P2 is assigned to 1. 1 is assigned to 1. So this becomes P3 of 1. And P3 of 1 is the image of 1 under the function P3. You find the image of 1 under the function P3. This is P3. And 1 is assigned to 2 under the function P3. Thus, the composition of P2 and P3 assigns 1 to 2. Next, we find the image of 2 under the composition of functions P2 and P3. By definition of composition of functions, the P2 circle P3 evaluated at 2 is equal to P3 of P2 of 2. And we find the image of 2 under the function P2. This is P2. And 2 is assigned to 3. So this becomes P3 of 3. And we find now the image of 3 under the function P3. What is that number assigned to 3 by the function P3? And this is P3. 3 is assigned to 3. Hence, P3 of 3 is 3. Therefore, 2 is assigned to 3 by the composition of functions P2 and P3. And finally, we find the image of 3 under the composition of functions P2 and P3. By definition of composition of functions, P2 circle P3 of 3 is equal to P3 of P2 of 3. We start by finding the image of 3 under the function P2. Or what is that number assigned to 3 under the function P2? This is P2. And 3 is assigned to 2 under P2. So this reduces to P3 of 2. And under the function P3, what is the number assigned to 2? This is P3 and 2 is assigned to 1. Thus, under the composition of functions P2 and P3, 3 is assigned to 1. 3 is assigned to 1. Now, by inspection of these 6 functions, what is that function where 1, 2, 3 are assigned to 2, 3, 1 respectively? And it is P4. P4 is the function that assigns 1, 2, 3 to 2, 3, 1 respectively. Thus, the composition of functions P2 and P3 is equal to P4. Now, if you want to do away with this part of the solution, you can easily find this function P4 in this way. You start with 1. 1 is assigned to 1. And then 1 is assigned to 2. So we have 2. Next, 2, you start with P2. 2 is assigned to 3. And 3 in P3 is assigned to 3. Next, we find the image of 3 under the composition of P2 and P3. We start with P2. In P2, 3 is assigned to 2. And in P3, 2 is assigned to 1. And this function from 1, 2, 3 to 2, 3, 1 is P4. Next, we find the composition of these 3 functions. Because composition of function is a binary operation, we can only combine 2 functions by composition of functions 2 at a time. Therefore, to get the composition of 3 or more functions, we have to group 2 functions at a time. And there are 2 ways by which we can do the grouping to find the compositions of P5, P4, and P1. the first way is to first get the composition of P5 and P4, and then combine the result with P1 by another composition of functions. Or the other way, you group P4 and P1, you get first the composition of functions P4 and P1, and the result you get the composition of P5 and the composition of the first two functions that you group. And we start with the first way, we group P5 and P4. The function P5 is the function from 1, 2, 3 to 3, 1, 2. And we combine function P5 with function P4 by composition of functions. And P4 is the function from 1, 2, 3 to 2, 3, 1. And the result of this composition, we combine with the function P1. Defined by this function where the elements 1, 2, 3 are assigned to 1, 2, 3. P5 is a function from set S to set S, and P4 is a function from set S to set S. Therefore, their composition is also a function from set S to set S, except that we do not know yet the images of 1, 2, 3 elements of S under the composition of the functions P5 and P4. And that's what we will find now. We start with 1. From P5, 1 is assigned to 3 by P5, and 3 is assigned to 1 by P4. Therefore, 1 is assigned to 1. Next, 2 under the function P5 is assigned to 1, and 1 under the function P4 is assigned to 2. And 3, we find the image of 3 under the composition of functions P5 and P4. Under the function P5, 3 is assigned to 2. And under the function P4, 2 is assigned to 3. And this result, we now combine with the function P1. This function is a function, this composition of the functions P5 and P4 is a function from set S to set S. And also P1 is a function from S to S. Therefore, the composition of these two functions is a function from S to S, where the domain is the set S with elements 1, 2, 3. And we find the image of 1 under the composition of these two functions. 1 is assigned to 1 by this function, and 1 is assigned to 1 by P1. Therefore, 1 is assigned to 1 by the composition of these two functions. Now we find the image of 2 under the composition of these two functions. In the first function, 2 is assigned to itself to 2. In the second function, 2 again is assigned to itself 2. And finally, we find the image of 3 under the composition of these two functions. Beginning with the first function, 3 is assigned to 3. And under the second function, 3 is assigned again to itself 3. And this function that assigns 1, 2, 3 to 1, 2, 3 is the function P1. Therefore, the composition of the three functions P5, P4, and P1 is P1. Now, we will do the other way of finding the composition of these three functions P5, P4, and P1. But now, we group the functions P4 and P1. We get first the composition of functions P4 and P1. And the result we combine with the function P5 by composition of functions. Now we find the other way of finding the composition of functions P5, P4, and P1 by grouping P4 and P1. By this means that we find first the composition of functions P4 and P1, and the result we combine with the function P5 by composition of functions. P5 again is the function that assigns 1, 2, 3 to 3, 1, 2. P4 is the function that assigns 1, 2, 3 to 2, 3, 1. And P1 is the function that assigns the set S, the numbers 1, 2, 3 to 1, 2, 3. The function P4 is a function from set S to S. P1 is also a function from set S to S. That is, the codomain of P4 is the domain of P1. Thus, the composition of functions P4 and P1 is a function with S as a domain and S as the codomain. So the domain of the composition of functions P4 and P1 is the set with numbers 1, 2, 3. Except that we will now find the images of these numbers 1, 2, 3 under the composition of functions P4 and P1. We start with 1. The image of 1 under the function P4 is 2. And the image of 2 under the function P1 is 2. So 1 is assigned to 2. We find the image of 2 under the composition of P4 and P1. We start with finding the image of 2 under the function P4. 2 is assigned to 3 by P4, and 3 is assigned to itself by P1. We now find the image of 3 under the composition of functions P4 and P1. The image of 3 under the function P4 is 1, and the image of 1 under the function P1 is 1. Therefore, 3 under the composition of functions P4 and P1 is assigned to 1. This function is a function from set S to set S with elements 1, 2, 3. This is also a function from set S to set S with elements 1, 2, 3. That means that the codomain of this function is the domain of this function. Therefore, the composition of this function and this function is a function from set S to set S with domain S and having the elements 1, 2, 3. Now we find the images of 1, 2, 3 under the composition of these two functions. We start with 1. The image of 1 under this function is 3. And the image of 3 under the second function is 1. Therefore, 1 is assigned to itself 1. We now find the image of 2 under the composition of these two functions. Beginning with the first function, the image of 2 under the first function is 1. And the image of 1 under the second function is 2. Therefore, 2 is assigned to itself 2. Next, the image of 3 under the first function is 2, and the image of 2 under the second function is 3. Therefore, 3 is assigned to itself 3. And this function that assigns 1, 2, 3 to 1, 2, 3 respectively is the function P1. But this is the same function that we obtained when we get the compositions of functions for P5, P4, and P1. But we group the first two functions first, P5 and P4. Therefore, we have shown here that regardless of the grouping of functions, the composition of three functions is the same. When we group the first two functions, P5 and P4, and the result we combine with P1 by composition of function, we obtain P1. And in this result, we group the last two functions. We get first the compositions of functions P4 and P1. The result we combine with P5 by composition of function, and we obtain the same result. So we say this particular example satisfies the associative property or the associativity property. Actually, in general, the permutations, the functions defined by permutations of the elements of a set satisfy the associative property under the operation composition of functions. For your practice, please try the following exercises. In the following exercises, you will make use of the following functions from set S with elements 1, 2, 3 to the same S with elements 1, 2, 3. But the elements of the domain S are assigned to the same elements of S by use of permutation. For this function P1, the elements 1, 2, 3 of S are assigned to the first permutation of the numbers 1, 2, 3, which is 1, 2, 3. In the second function P2, As we said earlier, the domain is S, and the elements of S 1, 2, 3 are assigned to the numbers in the second permutation of the numbers 1, 2, 3, which is 1, 3, 2. And for the sixth function, P6, or P sub 6, the elements of the domain 1, 2, 3 are assigned to the numbers 3, 2, 1, which is the numbers in the sixth permutation of the numbers 1, 2, 3. And you will make use of these functions defined by permutations of the elements of S to find the following. Number 1, find composition of P2 and P5, or P2 circle P5. And also find the permutation of P5 and P2, or P5 circle P2. And you check if the commutative property is satisfied. Number 2, find the composition of the functions P1 and P3, or P1 circle P3. Also find the composition of functions P3 and P1. And again, you check if commutativity is satisfied by composition of functions. Number 3, find the composition of functions P3 and P4, or P3 circle P4. Also find the composition of functions P4 and P3. And again, you check if composition of functions is satisfied. If commutative property is satisfied by composition of functions. 4, find the compositions of the three functions P2, P5, and P3. And again, as we did in the example earlier, you can find the composition of these three functions in two ways. And you do the two ways and you check if the associative property is satisfied by composition of functions. Number 5, find the composition of functions P4, P1, and P2. As with number 4, find the composition of these three functions in two ways. By the two ways correspond to the two ways of grouping two functions at a time from these three functions given, and check if associativity property is satisfied by composition of functions. And finally, find the compositions of these four functions, taking note that you can only find the composition of two functions at a time. So you take two functions at a time and combine the composition of two functions with the composition of another two functions. And that completes our lesson for today. And we will continue these permutations, these functions defined by permutations of the elements of a set in the next lesson for the group of permutations. And thank you for joining me in my class today in Abstract Algebra.